All right, let's get started. Thank you first of all, I want to thank all the organizers for putting up this event. It's really great to be here. It's my first time in Slovenia, and it's great. My name is Tang, and I'm from the Livepeer team. And just a side note, I am live streaming this talk right now at ericxtang.livepeer.tv. So if you go there, you'll be able to see the stream live. We recently launched the protocol, actually last week, on the Ethereum mainnet, and it's been an exciting time here. So what I'd like to talk about today is a specific component inside Livepeer, which is the scalable, decentralized video transcoding infrastructure that we're building. Can I have a show of hands and see who here knows what Livepeer is about? All right, cool. Roughly half the room. So Livepeer is a decentralized video live streaming platform. And the idea here is that instead of using a traditional centralized service provider that runs on AWS, we allow anyone to bring their hardware and join the network and in a decentralized way do video live broadcasting on the internet. And there are a few problems in this whole space because the end-to-end video broadcasting system is quite a complex system, right? So one problem that I'm going to talk about specifically today is transcoding. And for people who don't really know what transcoding is and why it's important, when we are watching a video on the internet, so say you go to YouTube and watch a video, there are many different bit rates and many different formats of the same video that are available in YouTube, so that when you're walking outside with a cell connection, or when you're sitting at home with a 10 gigabits fiber connection, you can always view the video in the best quality that's available to you at that moment. And it also accounts for many different devices, many different types of players. So when you upload that one video into YouTube, actually one of the first things it does is that it transcodes that video into many different bit rates and many different codecs, so that anybody in the globe can watch that video, right? And that transcoding job is very expensive from a computation standpoint. In fact, YouTube is the #1 largest CPU consumer in the entire Google infrastructure because people are uploading thousands and thousands of hours every hour, right? So this is a workflow called adaptive bitrate streaming. And the idea is that as you're playing the video, depending on your bandwidth at the moment, your video player is able to switch up and down the resolution based on where you are. And this is basically how video is able to play online with a very smooth playback experience. So today we can. Today we do video transcoding in a centralized way, right? So we host a service on Amazon or on a cloud-hosted service. We stream the video from our phone or from a laptop, from any camera, into the video, into the hosted service with some video protocol, and then it gets transcoded and then gets sent somewhere else. But in a decentralized workflow, what we want to do is we want to have anybody be able to put their hardware into a network and do the video transcoding for anybody on the other side of the open market who wants to get their video transcoded, right? And why is this powerful? This powerful is because #1, it gives open access to anybody who can provide hardware, right? So that means anybody who has any kind of computation capacity sitting around can join this network and provide value and be paid in exchange. It's dynamically scalable based on supply and demand, and this is a very important concept because video live streaming is notorious for the peaks and valleys that it has. When a popular event happens, many people want to watch the same stream, and usually the network is not being used that much. But as a provider of a streaming service, you end up having to always maintain the headroom because you have to account for the peaks. And that means you're always spending money on hardware that you're not using, right? But with this dynamically scaling decentralized computation cloud, essentially all of the resources will be used at a higher capacity, and as the demand of the network grows, the capacity of the network grows. And thirdly, the important thing here is that it can be trustless and anonymous, so that anybody who wants a video to be transcoded can trust anybody else on the network to do the work as long as they go through the protocol. So if we look at Livepeer as a transcoding market, this is what it looked like. I showed a picture similar to this in DevCon and EdCon, but this version is looking at just the transcoding piece. Right, so just to walk through how the protocol works quickly. First, the transcoder would advertise the capability and the price. So for example, it says, I'm able to transcode this one video from this bit rate into this many bit rates, right? And then this is the price I charge for doing this work. And any transcoder can kind of come in and do this and advertise their capability with the smart contract. And after that, a broadcaster can come in and say, I have a video and I want it to be transcoded, and create a job on chain. And when this happens, the job will be assigned to the transcoder, and the in a pseudo-anonymous, in a pseudo-random way, but with the price matching. So when the job is assigned, the broadcaster can start streaming the video into this video storage. And at the same time, the transcoders can start loading the video from the storage and start doing the work. And as it's doing the work, it's generating what we call claims of the work that it has done. Basically, it includes the signature of the broadcaster plus the hash of the results that the transcoder has done. And as it's gathering these claims for every single video segment, at some point, it writes a transaction back on chain with the Merkle root of all the claims that it has done, and essentially committing to the work that it has done. Right. And then also at the same time, the transcoder will write the result back into the video storage so that the video can be consumed by anybody in the world. And at some point later in time, a verification mechanism is going to be triggered by the smart contract. And this verification mechanism pseudo-randomly picks certain numbers of segments. And the segments have to be checked in the verification mechanism. And I'm going to get into that later. And the idea is that because the transcoder has already committed to the results via the Merkle root, if the transcoder comes back, if the verifier comes back with a different result, it means the transcoder has done the wrong work, and they will be punished. And that's how we make sure that the system itself is trustless, and you don't need any reputation to participate. So if we look at video transcoding, though, it's a form of parallelizable off-chain computation, right? Basically, something that cannot fit onto the Ethereum virtual machine. We have to basically any kind of computation like that. We have to do it off-chain, and then through some verification, do that on-chain just to verify. So if we right now, we're going to talk about some of the interesting problems that we're working on. So if we go back here and look at this picture, we can see that the transcoder is doing the work, but it's doing the work kind of based on the assignment of the smart contract, right? And that's kind of based on the job that's coming in. And the problem here is that there's not necessarily a lot of scale in this sort of workflow because the transcoders are kind of being assigned jobs, and they have to do the jobs, and they kind of have to wait for the next job to come in. So instead, what we're working on right now is scaling this architecture through what we call a transcoding race. And what that is instead of having one transcoder to do the job, we have a role called an orchestrator. And what the orchestrator does is that it will act as the transcoder as it is today, and it gets the job, and then it will make the work available so that multiple transcoders can do the same job. And they have to race to get the job done. So whoever gets the job done quickly and correctly wins that race, right? So imagine this in the concept as a framework of like mining, right? The idea is people are competing to get the job done, and then the winner of that competition gets the reward. In fact, because transcoding happens so quickly, maybe the losers who still get the right answer still get some sort of reward based on kind of like an uncle block. Yeah.
Yeah. So for the losers, is that still really profitable for them? Like, because it seems like it's a lot of work. Would there be much incentive for them to engage in this if they're getting a pittance? You know?
Yeah. So the idea here, right, is when you have, like, imagine you have some transcoding, some computational resource. What you want to do is you want to kind of spread out the resource so that you're not really doing work for one particular job, but you are doing small chunks of work for many jobs, right? And if you spread out the risk, it means the entire system is much, much more scalable. Yeah, so similar to like if you're running like nice hash on your computer or something, right? You're like mining many chains at the same time, right? Yeah.
It's an expansion function for cost for you.
Sorry?
It's an expansion function for cost for you. You can't compete with Amazon if you do this. Your expansion function is very long.
You see that as a consistent progress, but this might only happen with the startup stream. So, like in the first 30 seconds or 44 seconds, you probe the participating transcoders if they really are able to do the job. Try to prove their performance, try to prove their quality, and prove their timing. And only those who really did it then in time would be allowed to do the job. We could now have one or multiple or redundancies to continue, but that's now up to the user. He could decide. If he has a mission-critical stream, he might want to run multiple redundancies. If he has like just watching his puppies at home through his phone, right, then he doesn't need redundancies. We do this because we want to allow the transcoders to fail. We want to build a network where it is okay for any participator to really like lose power, like crush the CPU, everything goes up in flames, so the stream still continues. But yeah, it doesn't have to have a lot of time. And I think it's going to be crazily more affordable than AWS. We see that like a single NVIDIA card could do a job per day that's about 200 times less cost intensive than AWS transfer services. That means that with a single NVIDIA card, you could basically render as much videos as like 200 times the amount that you would get for the same price from the AWS service.
How does the cost scale with scaling the network? For example, for now, let's say I use my computer, I don't know, an hour a day. If I rent it out to the network, say it's going to run 12 hours a day, my costs and my monetization rise. So how does this price rise with scaling the network?
May I do?
Yeah, sure, go for it.
So in general, you would have like facilitation costs, of course, that is steady. With hashing, cryptocurrency hashing, you would have a lot of electricity costs. You don't really have this if your PC is on idle for a video compression. So basically, the amount of electricity you would use for that idle time is a lot less than during the computation itself.
Is the transcoding job always what? Deterministic. Good question. I'm gonna get to that later in the presentation. Yes. So there are many different scenarios of verification that we can talk about. But here, what I want to kind of touch on this right here is the scaling factor kind of comes from a crypto native way where people are competing to do the computation and being rewarded from that competition, and that incentivizes computation efficiency, and it incentivizes low latency, which is needed for video live streaming. Right? So if we look at this generalized computation market, right, the problem here really lies in decentralized verification, right? So the work here has to be verified, and that's kind of the tough part, right? Because now we're trusting any anonymous hardware on the internet to like do the work for us. How can we trust that it's correct? So there are a few ways to do this. One is simply playing a shelling game, and it's a fancy word for saying do the computation multiple times and then vote at the end to see who got it right. And then the people who didn't get it right get punished based on how wrong they actually are. Right? Now, this works well if you have a computation that's hard to be broken down into small parts, because you end up having, because if that's the case, if you want to verify it, you would have to do it again, right? But the bad part, of course, is that it's inefficient, and most likely it will never reach the efficiency of a centralized system who only has to do the work once, and that's it. So another way to do it would be to say, get the requester to verify the work, right? And that is to say, if I want to get my video transcoded, I will verify myself that the video has been transcoded correctly, and I can say the result is wrong if I decide it's wrong, right? Now, it's okay if you have a requester that's able to do the work already. Like imagine if I tell someone else to do my homework, and then if I don't trust them, I can just do my homework again. But then that requires me to do the homework, right? So if I have some embedded device that needs the work to be done, maybe the device itself does not have the capability to do the work. Another problem here is there are some economic attacks. Imagine, it doesn't apply in all cases, but imagine if you have a crypto scheme where there are rewards being minted for doing the work. So it's not just the fees, right? Imagine Bitcoin mining, you have the block reward and you have the transaction fees. So if the requesters are the ones that are verifying the work, essentially you open up to a Sybil attack vector where the requester can collude with the workers so that the requesters can say, I'm going to just put in a bunch of work, and I'm always going to say the work is correct for a certain worker, right? So that way, I'm artificially inflating the amount of work that the worker has done. Therefore, the worker will get a lot more reward. And even if there's no inflation, maybe there's a reputation attack, because in a work system, the workers who have done more work appear to be better workers, right? Another way to do this would be to use a trusted computation oracle. So something like the Intel SGX can give you a cryptographic proof of the work that it has done, right? And of course, it's nice because it's simple, but it's also centralized. But it's actually not as bad as we think, right? Because if we also add decentralized governance to this mechanism, at least we have the ability to swap out these computation oracles and put in other ones so that we can kind of protect ourselves against kind of like a state-level censoring effort or something like that. The solution that we're working on, and we're pretty excited about, is this decentralized verification mechanism. And we're collaborating with the TrueBit team a lot on this. Anyone here know show of hand, know what TrueBit is? All right, I'll explain. So TrueBit is this idea of remembering all the computation steps that have been done in a piece of computation, right? So what they have done is they've built this custom interpreter that compiles a piece of computation down to its steps. Imagine if I have, if I compile a program into assembly, and every assembly instruction is a step, right? And what you can do is, for every single step, calculate the hash of that step, and then create a Merkle root at the end and commit that Merkle root on chain. So now, imagine if I was a solver and I did that, I would have effectively committed my result on chain and also committed every single step of my computation on chain. Now, and by the way, because it's on the blockchain, anyone can see this happening, right? So if I'm someone else and I see some computation being done, I see the result being committed on chain, I know what the inputs are. I can do the computation myself and see if my result matches that. And yeah.
As long as you have the data, right?
Right, yeah, you have to have the data, correct. So when and the data can be also committed as a hash on chain, right? So when that happens, not only can I say, oh, my result is incorrect, we can deterministically decide who has the right result by doing this challenge game that essentially is doing a binary search that gets to the exact computation step that me and somebody else differs. And then, since this is an interpreter that also lives in the EVM, I can submit the single computation step into the EVM and do the single step on the EVM to get the deterministic right result from the EVM and decide who did the right work, right? Now, it's too expensive to do the entire computation on the EVM, but if we just narrowed it down to a single step, it becomes doable.
It applies that transcoding, if any possibility to transcode is deterministic.
Exactly, yeah. It has to be deterministic in this case.
Random results and transcoding.
There is. Let me get to that in a minute. So if you want to, so there has been a proof of concept that's built. If you want to check it out, it's at this URL. So now we're going to get to the non-deterministic computation verification, right? So in video transcoding, sometimes the work is not deterministic. Imagine, especially when you're running on a GPU because of the floating point calculation. So here we need to use other types of verification instead of bitwise verification. So these are things like video fingerprinting, which is basically calculating the kernels on the images, so that you can what you can do is compare two images with different resolutions to see if they're the same image, right? And this is we've been doing some research in this area. Another way to another area in here is the video quality score. So how good is the video? So there's been a lot of research done in this over the year as well. The exciting thing that I'm personally excited about is VMAF that came out of Netflix. And also we can use video resolution, video size, to basically decode the video and try to understand all the different aspects of the video to decide whether this is an acceptable result, right? And the future of this verification scheme is really to open it up so that it's customizable, so that a requester of the work can pick the type of verification that they want to be done, right? So right now, in the current version, the protocol kind of picks the verification method for you, which is this like bitwise decentralized verification. But in the future, I should be able to write a verification method myself. And if people like my verification method, they should be able to pick my method and use that instead. So that was the verification problem. Anybody have any questions before I move on? All right. Another big issue here, which is an open problem, is the data availability problem, right? And this is hard because imagine if I'm a transcoder and I'm competing with all the other transcoders on the network. I always have the incentive to make the data not available for them. So I will win all the time through a variety of different attacks, right? And in fact, this is a problem that exists in Livepeer, in TrueBit, even in Ethereum itself, right? This data availability problem is something that hasn't been solved yet. So that's why I'm very excited here at Swarm. Maybe Swarm will solve that problem for us via the swap, sort, and swindle scheme. So that's all I have.